Hello everyone, I'm Jinyang Guo from the University of Sydney. Today, I would like to share our work, Multi-Dimensional Pruning, a unified framework for model compression. This work is collaborated with Dongxu and Wanli Ouyang from the University of Sydney. Although deep neural networks have achieved many successes in computer vision, it is still a challenging task to deploy these networks on mobile devices. Model compression techniques aim to compress the deep model and deploy them on these devices. It can be roughly categorized as quantization, tensor factorization, compact network design, and channel pruning. However, the existing methods do not explore two redundancies, the temporal-wise redundancy and the spatial-wise redundancy. Here's a video clip of skydiving. We can see the 4 frames in this clip are almost the same. This indicates the temporal-wise redundancy exists in a video. Also, there is almost no information in the background, which indicates there are spatial-wise redundancy. If we downsample these 4 frames along the spatial and temporal dimensions, we can still easily recognize the people are skydiving in the downsampled image. This indicates we can reduce the redundancies on the spatial and temporal dimensions by the downsampling operation. To this end, we propose our multi-dimensional pruning framework, which can simultaneously reduce the spatial or spatial-temporal and channel redundancies. Moreover, our MDP method is a unified framework that can prune both 2D CNNs and 3D CNNs. Our MDP approach can be divided into 3 stages: the searching stage, the pruning stage, and the fine-tuning stage. In the searching stage, we firstly construct an over-parameterized network. In this figure, we use pruning a 3D CNN to illustrate our method, and pruning 2D CNNs is a special case of pruning 3D CNNs. It shows one convolutional layer in the original network. The depth of each block represents the length along the temporal dimension. We expand the original layer to several parallel branches to construct an over-parameterized network. In each branch, we firstly average pull the input tensor along both the spatial and temporal dimensions. Different branches have different downsampling ratios. There is no average pulling operation in the first branch because we use the downsampling ratio of 1 along both the spatial and temporal dimensions. Then we perform the convolution operation on the downsampled tensors. We use a gate to scale each channel. These gate values indicate the importance of channels and will be used for channel pruning later. After that, we upsample the gated tensor to its original resolution to ensure there is no shape mismatch for later aggregation. We aggregate the tensors from different branches by using the weighted sum of them. The weights represent the importance of branches. We jointly learn the parameters for the convolution operation, the importance of channels and branches in this stage. Here is our training objective function. We aim to learn the parameters for convolution theta, the importance for branches lambda, and the gate values g. LC is the standard coarse entropy loss for classification task. LST is the penalty to introduce sparsity on branch importance. LGate is the penalty to introduce sparsity on gate values. When training the network by this objective function, the importance scores of many branches and channels will be close to 0, and we can safely remove these branches and channels later. After finishing training, we prune the network in the pruning stage. We only select one branch with the largest importance score in each layer. We also prune channels with small gate values in this branch. After pruning, we fine-tune the network to recover from the accuracy drop. Here is our results for pruning 2D CNNs when pruning VGG, ResNet, and MobileNet. Our MDP approach achieved highest accuracies with comparable number of flops. This is the result for pruning 3D CNNs when pruning Z3D and I3D. Please come to our poster for more details. Thanks.